In this final video, we're going to look at how a cyclotron works, which is a very important application in this course. Okay, so let's talk about how a cyclotron works. This is both the application from the motion of charged particles in an electric field and the motion of charged particles in a magnetic field. And I've combined the electric field stuff here and the magnetic field stuff here all together. I just think that's a more sensible way to do it. So there's a lot on this slide, and I apologise a little bit for that, but I think it's easier to keep it all on one slide. So, what does a cyclotron look like in essence? And we've got a diagram here of a cyclotron. It contains semicircular metal Ds, so these are our metal Ds. They look like the letter D, hence the name Ds. This is, if you like, a top view, cross-sectional view. We've got basically a top and a bottom, a north pole and a south pole. And in this case, the magnetic field is directed downwards into the page. The charges move in this space between the two plates of the Ds. We've got another D on this side, similar, just with the, if you like, the reverse D shape. Once again, the magnetic field there is directed in a downwards direction for the sake of this example. All the space in between here is evacuated so that we don't have air molecules that the ions can collide with that are being produced and lose energy. We'll come back to that in a sec. And then we have a voltage, an alternating voltage, which creates an electric field, which is applied between this plate and this plate, or this side and this side of the Ds, and will be used to accelerate our ions. We'll go through that in a sec. So, might just cover a few of these little dot points, not all of them, but a couple of these dot points before we start. Explain why there is no electric field inside the Ds. Well, the reason there's no electric field inside the Ds is because they are a hollow conductor. So you don't get an electric field inside a hollow conductor. So we only have an electric field in the space in the space in between the Ds. Explain why the cyclotron must be evacuated. I just mentioned that before. Otherwise, the ions would collide with air particles and lose energy. So otherwise, ions collide with air and lose energy. Okay. So, let's start talking about what happens to an ion. And this is, I guess, one of the things we need, an ion source. In the middle of this, this will often be protons. These protons are introduced into the middle of the cyclotron. And we can imagine, just for argument's sake, that let's say this just starts out as they're introduced as being the negative side. This is the positive. This ion will get attracted, because it's positively charged, towards the negative. As it attracts it, work is done, so it gains energy. We can think of that in two ways. So this comes to a couple of dot points here. Describe how the electric field between the Ds can transfer energy to an ion passing between them. We can think of it as an electric field. We know that from the equations F equals ma and F equals EQ, that acceleration is equal to EQ on mass. So if you get a charged particle with a charge and a mass and put it through an electric field, it'll accelerate. Therefore, it'll gain speed, gain energy. If you want to calculate how much energy it gains, rather than doing its acceleration, which is this dot point here, calculate the energy transferred to an ion each time it passes between the Ds. Then we use the formula, the work done. So the energy gained is the work done equals the charge times the voltage. So Q delta V. So, accelerates, gains energy, whichever way you want to think of it. Then it hits this area here where there's a magnetic field and no electric field. Magnetic field, to use our right hand palm rule, in fingers into the page, thumb in the direction, positive charge, so it comes out of the palm at 90 degrees, constantly at 90 degrees, and that causes that to rotate in a semicircular path to there. Then when the ion gets back to here, or by the time the ion's got back to here, we flip, so this is an alternating voltage, so flips to the other way. This positive is now going to be attracted towards this new negative. Boom, fires straight across there. Then it does a similar thing, magnetic field into the page. Thumb in the direction of the current, flips it around. Current reverses again by the time it gets to here, gets accelerated, so it gains more energy. So it's in its third trip across this electric field now, so it's gaining more and more energy every time across the electric field. Now, obviously as it gains energy, it gains speed, so its velocity increases. If its velocity increases, the radius increases. We just derived that formula on the last slide. So the radius gets bigger and bigger, comes back here, gets some more energy, shoots across there, and then eventually it reaches the outside, and I'll exaggerate a bit here, and it can be fired off at some target to make a new isotope to hopefully help diagnose cancer or some other serious illness. So that's what this is, diagnosis, or produce isotopes, the diagnosis of particularly cancers. I think they mainly use them for. So it does, yeah, the way we do that is by producing radioisotopes. The last topic of the year, we're going to go talk more about radioisotopes, so we might revisit some of the things that happen in a cyclotron when we do that topic. So the only one I've really missed there, but hopefully I've explained as we go on, describe how ions could be accelerated to high energies if they could be made to move in a circular path inside the Ds, so they could repeatedly move across the electric field, once across, twice across, 3 times across, 4 times across, and we could go on and on. So they repeatedly moved across the field, the direction of which was reversing every half revolution. So this needs to alternate every half revolution. So hopefully that's given you an insight in how a simple particle accelerator known as a cyclotron works. But now there's a couple more things we need to look at, more related to the magnetic fields. And I guess we've already described the direction of the magnetic field needed to deflect the ions in a circular path. In this case, to make them turn up, has to be downwards. If it was upwards, they would have just spin the opposite way around. We need to show the period of the circular motion of an ion is given by that formula, and hence is independent of the speed of the ion. Might talk about that first. The period of revolution here, which is related to the period we need to alternate this potential difference to keep accelerating them, only depends on the mass of the particles, the charge, and the magnetic field strength. It doesn't depend on how fast they're going. That's really neat, because that means that we can basically change this at a constant rate. So we can have a constant stream of ions coming in and basically being accelerated through this. If this needed to change as this moved further and further out, it'd make the control of the system much more hard. You could only have sort of one ion moving through there at a time. So that's why that's important, and we better quickly derive that relationship as well. From our formula sheets, we can see V equals, for circular motion, 2 pi r on period. And we also know that from the last slide, R equals mv on qb. We can rearrange this formula. I won't do that to get, I'd hope you're getting confident now with your algebra. So I've just times q by e by both sides and then divided by m. And if we then equate these two things, we get 2 pi r on t equals QBR on M. We want to work out period, which is a bit of a pain because it's at the bottom, so let's times both sides by period. Then we've got to get rid of all this stuff, so we're going to times both sides by M and divide both sides by QBR. QB's cancel and the R's, and we get left with period equals 2 pi I made a mistake there, but see, I've got an R and an R there, so they cancel. I just could have cancelled the R off both sides. 2 pi M on QB. So I didn't have to divide by R on both sides to get rid of the R's because I had an R on both sides. But either way, it's okay. I'd like you to work through that derivation anyway and check it for yourself. I think you find it's not too difficult. Finally, we need to think about this relationship here. Well, let's go through what we need to do. Using the relationship for kinetic energy and the radius one that we've just derived, show the kinetic energy K of ions emerging from radius emerging at radius R from a cyclotron is given by that formula. We'll do that in a sec. Before we do that, we'll talk about why it's important. Use the relationship there to show K is independent of the potential difference across the D's, and for given ions depends only on the magnetic field and radius of the cyclotron. So the energy this ion comes out of here at the end depends only on its charge, the magnetic field strength, the radius and the mass. Doesn't depend on this voltage that we're using. What happens if we have a low voltage here? Ions will only gain a little bit of energy each time, so they'll just keep going around and around, just gaining a little bit more, 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 doing lots and lots of laps before they come out. If we have a higher voltage, we don't get any more energy at the end. All that happens is it shoots through here, it's got a lot more speed, so it only shoots around here, boom, round, round. It basically gains more velocity, gains a greater radius each time, so it does a lot less revolutions, shoots out of here earlier, for lack of a better term, because it hasn't passed across the electric field as many times. But with a low voltage, it'll still get to the same energy, it'll just have to go through there a lot more times, because it'll gain less speed, so its radius will be less, so it'll do a lot more laps. That's pretty important. You also need to solve problems using those two relationships. But just to finish on, I'll quickly show you that derivation. Let's go to purple. So once again, we need to know that K equals a half mv squared. Now we've got to rearrange this formula for here down to this one here. So we've already done that step from before, so I'm just going to copy this formula here. So that's just a rearranged for the radius formula. QBR on M. And basically we're going to substitute that equation into there. So we get K equals a half times M times QBR on M squared, which equals a half MQ squared B squared R squared on M squared. So M squared is M times M, and that's an M, so we can basically cancel out that, and we get left with K equals Q squared times B squared times R squared divided by 2M as required. And I'm just going to make it because these videos have got to be less than 15 minutes long or YouTube doesn't like them. So that is how a cyclotron works. Cheers.